Hello, and welcome to this uh, tutorial on basic species distribution modeling in R. So we'll jump right into it. The first thing we're going to need to do some species distribution modeling is some occurrence data. So I'm getting mine from this online database, VertNet. I'll be downloading data for the Blandings turtle, an endangered turtle native to eastern North America. If you have another species you'd like to work on, you can do that, or you can follow along with this data set. So here's what the data set looks like on VertNet. We're going to go ahead and download it. So if you have a large data set, you may be required to send it a link to your email. I've already done this, so go ahead and send that link to yourself if you need to. We'll be doing this analysis in the R statistical software using the RStudio interface. So you want to make sure you have a recent version of those on your computer in order to do this. So the first thing we need to do in our workspace is to download all of the libraries that we're going to be using today. So in order to do that, you're going to go to the Tools tab, Install Packages, and to download the packages, the 5 packages we have, just type in the names. I've already done this. Make sure, as always, to install the dependencies to make sure all your libraries are going to work properly. So like I said, I've already done this, so I'm not going to do it here. But now we're just going to go through and make sure all of those libraries get loaded into our workspace. All right. So moving on, next we need to import the data set that we downloaded from VertNet. It's a text file. So just open it up. All right. So there it is. That text file right there. We'll go ahead and open it. Here's just some settings for importing it into our workspace. So we do have a heading for each of our columns, and these are just basic settings for importing into R based on which kind of text file you have. We'll go ahead and import it. And there it is in our R workspace. So we need one more piece of data from the RGeos package, and it's just world boundary data to help us make our maps. So we'll go ahead and get that into our workspace as well. And we'll give our occurrence data worksheet a more workable name instead of that long string of numbers and letters. So we'll call it occurrences. All right, so the first thing we need to do is make sure that our Blandings turtle occurrences are in the place that we expect them to. So we'll go ahead and look at the plots and plot our points. So decimal longitude and latitude. Make sure you do that in the right order. Zoom in. Just make sure all of our points are occurring in a place that makes sense. So they're all in the eastern United States and Canada. We don't have any occurring in Asia or South America or any other place where we wouldn't expect to find them. So we'll just zoom into that area and get some settings for our map. So when we do some further analyses, we can concentrate on that area. So there we go. You can see it's all in the eastern US and Canada. All right, so we have a lot of data maintenance to go through since we're using a data set from an online database. So we want to look at our decimal latitude and longitude. And one of the problems we see right off the bat is that a bunch of these occurrences don't have any location data. So all those NAs. We don't want to use those. They're just clogging up space. So we're going to go ahead and remove those occurrences. So now you can see we're down from about 11,000 or 1,100 observations, just 223. So only 223 of our observations actually had data on location. Next up, we need to make sure that all of the points are in the place that they say they are. So we're separating or occurrences into US and Canada, you might want to go to an even finer scale and look at states and provinces if you want to publish this data. But here's our data from the US, and all of the points look like they are actually in the United States. So that's good. Now we're just going to do the same thing with Canada and make sure all the points that say they're in Canada are in fact have latitude and longitudes in Canada. Yep, all good. So we'll go ahead and move ahead. If you do have any points outside of where they say they are, you should go into your data set and manually remove them. So we'll make our data set from the different countries one again. You also notice that we're down to 147 occurrences from 217. So 70 of our observations did not have a place where we could georeference them. So we don't want to include those going forward. So next up, we want to remove duplicates from our data set. These are points that have the exact same decimal latitude and decimal longitude, so they're in the exact same spot. We don't want to have those. So looking at how many duplicates we have in this data set, we have 80. We want to make sure we get those removed. And just plot one last time to check out how that affected our distribution. Yeah, so we don't want to include duplicates because when building our final model, those can bias the results and make environmental conditions in one certain spot more important than they actually are. So these pretty much the same distribution here, looking good. Moving on. So we don't have any examples of this in this data set, but there are some data sets on VertNet that have fossil and captive records. We're only looking for actual observations in the wild, so we're going to go ahead and remove any instances of those. Once again, there's not any in this data set, but you may be using a data set that does have fossil and captive records. All right, one last thing to do before we make our species distribution model. So in our data set, we have points using multiple different coordinate systems. We want to make sure that they are all converted into the same coordinate system. So we have points using NAD27 and the long form of that name, North American Datum 1927. So what I just did there was pull those out and put them into a data frame together. We'll do the same thing for NAD 1983. Once again, there's some points using the long form of that name. And then the last one is WGS 1984. We also have some points that do not have a coordinate system recorded. Depends on what you want to do with this. Typically, WGS 84 is the standard that most GPS units use. So it's relatively safe most of the time to convert, to assume that those points are in WGS 1984. You may just want to double check that or not include those points if you're really concerned that they're not WGS 1984. All right, so in order to convert each of our different coordinate systems, we're going to convert them all into WGS 1984. So what we need to do is tell R that the decimal latitude, longitude, and latitude are coordinates, and then give those coordinates a projection. So for NAD 1927, that's datum equals NAD 27. And then last step, we want to convert those points into WGS 1984. So we just did that for NAD 27, doing the same thing for 1983. For the WGS 1984 points, all we need to do is assign them that WGS 84 datum. We don't need to convert them, so we'll just do the first two lines of that process. All right, and then we'll put them all back together into the same data frame one last time. Plot them, just make sure nothing weird happened. Make sure they're all in the right spot. Yep, everything looks as we expect it to. Alright, so now comes for the fun part. We get to make the species distribution model. So to do this, we're basing it mainly on bioclimatic data. We're going to import that data from the WorldClim database. I'll go ahead and pull that up right now. So what this WorldClim database is, it has a number of bioclimatic variables ranging from, you can see here, annual mean temperature, all related to temperature and precipitation throughout the year, and how those are related to each other. All things that might affect whether or not a species can survive in an area with a certain climate. All right, so we'll go ahead and import that data into R. I'll just give our plot a little bit more room and plot that climate data so you can really see how some of these bioclimatic variables are distributed. All right, so now we're going to extract the climate data from each of our observation points. So for each of those 19 bioclimatic variables in our data set, we're going to make a new data frame that takes the values of each of those variables for each of our observation points. So that's what that extract function just did. And now those points are going to be used to create our species distribution model using this bioclim algorithm. So there's multiple different ways to construct a species distribution model. This bioclim algorithm comes prepackaged in the Dismo package. It's really easy to use, so we're going to go ahead and stick with this one. Basically, it's looking at the median value for each of our bioclimatic variables, and the closer value is to that median value, the better habitat it is for that animal. So that's how the bioclim model works. You can always look at the help for more details. There's other ways you can use to construct a species distribution model, but those are topics for another video. So we'll go ahead and run this. All right, so now we have our species distribution model, and now we actually get to plot out where we would expect the Blandings turtle to show up. So what I just did there, I just created a raster set of predictors, and then we're using this predict function with that raster set and the bioclimatic model that we made using the bioclim algorithm to create a set of predictions, a raster of predictions of where we would expect this turtle to show up. So the last thing for us to do is to actually plot out these predictions and see what our species distribution model looks like. So I'll go ahead and do that. And there is our model out on the map. So the green areas are the places where there's really suitable habitat, at least climatically. And the gray and red areas are places where we really wouldn't think there's a large chance of finding this turtle. So that's pretty much all there is. We can compare it to what the actual known range is. We see it's doing pretty good. We might be able to improve on that with some more complex models, but that's for another time. So congratulations, you now know how to do some really basic species distribution modeling.